Yeah, even if your video is the best, you still have to take the test. So we want everybody to be focused and on task today. Alert. Test is tomorrow. Test looks a fair amount like this review handout. It doesn't look exactly like this, but many of the questions are similar. Particularly on the last page, though, I think you'll find the questions are reminiscent of what was on the review, but not really exactly the same. There are variations here and there, as always. You get to bring a note card, 3 by 5, both sides, even around the edge if you want. And you can bring a unit circle. I don't think you'll need any of its features, but if you take comfort from having it with you, you can certainly bring that along. So at the beginning of this test, we're talking about, yep.
Can I have a copy of that?
I don't have any more.
All right, that's all right.
It is online still. And we'll also find an answer key online and maybe a video if everything goes well. So the first question what we're doing is some operations on vectors using graphical techniques. So these vectors are represented as arrows on a piece of paper. The vectors are indicating with their length, the magnitude, and their orientation. And the arrowhead are important for showing what direction the vector is in. So to add vectors, what we're going to do is reproduce the original vectors that are up here at the question. So I'm going to reproduce to my best ability vector u. So I'm trying to match the length and orientation and get the arrowhead at the same end as I do on original u. And then v, I'm going to tack on the end like this. So the idea is, if you started at the beginning of one vector and walked down that path in the direction of the arrowhead, you'll find yourself at the beginning of the second vector. And if you walk down that path to its arrowhead, you have the end. And so I can substitute for this a third vector that begins where the first one began and ends where the last one ended. That's what we mean by adding vectors together. Now, the interesting thing that I don't have a chance to show here is that if I change the order in which I do this, if I start with vector v and add vector u, I'll end up with a vector u plus v that is the same length and the same orientation and direction as what I have here. Now, in answering a question like this, it is important to show me how you did it. So we'd see vector u and vector v being added together. Make sure you get this orientation of going tail to head, then tail to head. More importantly, though, I need to see this resulting vector shown. So it's not enough just to do this. I need to see this. And that arrowhead at the end is extremely important. Without that, I have a line segment. I don't have a direction. The arrowhead gives me a definite direction. So this vector in red really is the answer to this question. Important to have. Now, second question, negative u, means that I have a vector the same length and orientation as u, but going in the opposite direction. So I can simply draw an arrow that matches u's length and orientation, but has the arrowhead at the other end. And I'll label that negative u. 2v means that I'm going to have a vector that's in the same orientation as v, in the same direction as v, but twice as long. So I can do that freehand and say, okay, there's one v, there's another v, there's my arrowhead, that's 2v. Now, some people, when they do this, will say, I'm going to take two v's and add them together. That's great, but you still need to show me the resultant as a single vector. So that would be like this problem here, where I'm adding two vectors together to get the resultant. I can add these two vectors together and get this resultant. Finally, we've got u minus v, which is the same as saying u plus negative v. So I'll do something similar. I will sketch U and negative V. So I've drawn, for my second vector, one which has the same orientation as V, but has the arrowhead at the other end. And I position these so that if I start at the beginning of one and go to the head, I'll find myself at the beginning of the second one. I can go to its head. And the resultant will be the one that starts where U started and ends where negative V ends. So there's my final answer, U minus V. Questions? Right, question 2 is doing something similar, but we're using numbers. We have a couple of vectors, 1, 2, and negative 2, 3. And we're going to do these operations, but we're going to do it numerically. So with this one, I have 1, comma 2, and I'm adding to that negative 2, 3. And that operation consists of adding the x components and adding the y components and keeping it in vector form. So we've got negative 1, comma 5. Now, we also have to graph that. Now, vectors have a direction and a magnitude. They don't have contained in them some knowledge about a location. So we can place these anywhere we want on the grid as long as we have room. So this vector is going to go negative 1 in the x direction. That's to the left 1 unit. And then up 5 in y. We just need to make sure we've got room to do that. So I could begin this vector on the right-hand edge and say we're going to go to the left 1 and up 5. Which should take us up to there. So there's my line segment. The direction has us going up and to the left, so I'm going to put my arrowhead up there. Again, these aren't really vectors unless there's an arrowhead at one end, and it's the right end. So we're starting here, moving to there. And I'll label this as A. Negative U means we're going to be doing the negative of 1, 2. Which is the same as negative 1, comma negative 2. So to graph that, I can make another starting point here. We're going to go left 1, down 2. That's really not very good. There's my arrowhead. And I'm going to call that V. 2V means doing 2 of the negative 2, comma 3 vector, which is the same as negative 4, comma 6. So for that one, I need to pick another starting point. Let's say here. We're going to go to the left 4 units, 1, 2, 3, 4, and then up 6. 1, 2, 3, 4, 5, 6. There's my end. I'll put in an arrowhead there, and then draw the segment.
So you can start anywhere you want?
Yeah, I can. Now, somebody asked me in another class, what if I put like an x and y axes on this grid? And what if I start all these vectors at the origin? So it's kind of fanning out in all directions. And I say, that's fine. You could just as well do that as anything else. I don't do that here because I don't want to imply that you must do that. So this is the most sort of random way of doing it. Like I say, vectors don't have necessarily a location. Sometimes we form a vector from points that do have a location. So if we had point A and point B, we could find vector AB. And because we form that between 2 points, it's sort of an implied location. But really there isn't. It's just, how do you have to move to get from A to B? Question D, we'll do U minus V, which means 1, 2, minus negative 2, 3, which is, minding the signs, 3, negative 1. So we're going to go from a starting point to the right 3, down 1. There's my arrowhead. There's my line. There's my label. So I have A, B, C, and D. All right, question 3. Question 3 has a three-dimensional grid, so to speak. And there are two different things that we practice doing with a grid like that. One of them is plotting a point in three-dimensional space using a two-dimensional piece of paper. Another one is plotting a plane. So neither of these really work that well in 2D, but we have some tricks for doing it. And that's what this is about. So the first task is to plot point A. And I'm going to do that in three phases. I want to show how much it's displaced in the x direction, how much in the y, and how much in the z. And I'm going to do that by starting at the origin. I'm going to leave a trail. I'm going to first move 3 units in the positive x direction. So 1, 2, 3. And then I'm going to move 4 units in the positive y direction. Now, to do that, I'm going to move directly to the right, making 1, 2, 3, 4, a path that's parallel to the y-axis. That's another corner. And then I'm going to go up 2 units in z. So parallel to the z-axis, straight up the page, 1, 2. And I'll leave my final point there. So that point that's my end point, I'm going to label that as A, so that I know on this page with all this work that I've done, these line segments and intermediate points and so forth, you want to be able to tell me which of those is actually point A. So label it so that I know what you did. There are other ways to do this by making it like a rectangular box, but this is the quickest, easiest, I think the most direct way of doing it. Second task, plotting a plane. So here's a plane equation. And our trick for plotting a plane is to find the x, y, and z intercepts for the plane. To do that, we use the cover-up method, which I can't easily show you on the screen, but I'll describe it. So to find the x-intercept, that's the place where the y and z values are 0. So in that case, we have an equation that says just 2x equals 6. And I can solve that and say that the x-intercept is 3. For the y-intercept, I would set x and z equal to 0. And that gives me the equation negative y equals 6, which means that y equals negative 6. That's the y-intercept. On the z, we'll set x and y to 0, and we have the equation 3z equals 6, which means that z equals 2. So on my graph, I'll change color for that. I'll have the x-intercept is at 3, positive. Y is at negative 6, which is the end of my arrowhead on the left-hand side. This is 3, negative 6, and then positive 2 on the z-axis. And then finally, so this represents 3 points that lie in some infinite plane. I'm still not seeing it, so to help visualize it, I'm going to imagine that this is like a triangle that's opaque. And it looks like a piece of something that's tipped a little bit to the left and towards me. I can imagine that something is actually a piece of an infinite plane that has that same tip. It's tipped toward me and to the left. And so it's just a visual trick to make us think that it's a plane. So again, these two operations, if we're asked to do a point, make sure you do the right thing. If you're asked to do a plane, make sure you're doing the right thing. Two different processes. All right, so 1a, we have got a couple of vectors, u, which is 3, negative 2, and v, 4, 1. First question is find any vector that's parallel to u. So that means a vector with the same orientation. Could be in opposite direction, but the same sort of slope, if you will. And easy way to do those would be to say, well, let's take u and multiply. Let's make it longer. Let's make a longer version of u. It'll automatically have the same direction. So, for example, 2u would be parallel to u, and that would be 6, negative 4. We could also do negative u, which would be negative 3, 2. So those would be two vectors that are parallel to the original vector. Somebody in another class had a great suggestion. if you're afraid of doing arithmetic, you could say, pi u Oops. So you have a vector that's components are 3 pi and negative 2 pi. Well, that works. So kooky length, but still parallel. So there are multiple infinite correct answers for this question. Those are just some examples that work. Part B, are vectors u and v perpendicular? Explain your reasoning. So we have, some of you may notice that this idea of a two-dimensional vector is kind of reminiscent of slope, rise and run. And there may be a rule that you learned in the past for finding perpendicular slopes, negative reciprocal. So that process works here as well. Where that process is a little trickier is if you've got three-dimensional vectors. So for three-dimensional vectors, 3D vectors, we have another process that's maybe a little easier. And this is going to be a demonstration of that process on a 2D vector. So the idea here is that we want to take the dot product of u and v. One way of defining a dot product is that it's the magnitude or length of u times the magnitude of v times the cosine of the angle between them. If the angle is 90 degrees, the vectors are perpendicular. The cosine of 90 is 0. So what that means is the dot product of perpendicular vectors is 0. So one way of doing this is to say, if u is perpendicular to v, then u dot v will equal 0. So that's explaining our reasoning. Now let's figure out what u dot v is. So if I've got vectors in component form, it's easy to compute the dot product by multiplying the x components and adding to that the product of the y components. And if it's 3D, add to that the product of the z components. So u dot v equals, now I'm going to look up here my original vectors, 3 times 4, that's multiplying the x components, plus negative 2 times 1. And if I add that together, I'm going to get 12 minus 2, or 10. Therefore, u is not perpendicular to v, because the dot product wasn't 0. Okay, so we know, we haven't figured out what the angle is, but we know for sure it's not 90 degrees. If it had been 90 degrees, that dot product would have come out as 0. However, now that we know they're not perpendicular, we can go and find the angle between them. So to do that, we'll use this definition of dot product that says it's equal to the magnitude or length of u times the magnitude of v times the cosine of the angle between them, which we happen to know is 10, because we use this alternate method for calculating the dot product. Now, we want to know the angle between them, so we can solve this equation for theta. So cosine of theta equals 10 over magnitude u, magnitude v, like that. And furthermore, we could say that theta equals the inverse cosine of 10 over magnitude u, magnitude v. All right? Now, so this is something we can calculate if only we knew how to figure out the magnitude of u and the magnitude of v, which isn't that bad either. So magnitude of u, finding the length of a vector. If you know the components of the vector, that's like seeing the legs of a right triangle. And what you're trying to do is figure out the hypotenuse. So the Pythagoras theorem works here. You can do Pythagoras on the components and get the length of the vector. So in this case, we'd be doing the square root of the components of u squared. Let's see what they are. Oh, yes. 3 squared plus 2 squared, which equals the square root of 13. And the magnitude of v, Pythagoras again, 4 squared plus 1 squared, the square root of 17. So finally, I can run out of room here. Let's call this the inverse cosine of 10 over root 13 root 17. When you do this question, or something like it, make sure when you do this division that you're dividing by the product of 13, or root 13 and root 17. Protect that denominator in parentheses. When you do that calculation, make sure you're aware of parentheses. And the answer here is going to be 47.7. Yep.
And that's cosine, inverse cosine?
Inverse cosine, yep.
Oh, wait. You mean inverse cosine of 10 over root 13 times 17 is 47.7?
Yep.
Okay.
So we're evaluating this, taking the inverse cosine of it, and that gives us 47.7 degrees.
Okay.
And that's admittedly not a lot of room to do that question in. Question 3. We're back to a graphical question with vectors. Given vectors A and B, express the unlabeled vector. Well, heck, let's label it, shall we? C. Well, let's express C in terms of A and B. So, okay, so is C equal to A plus B?
No.
No. So A and B aren't oriented the correct way that I could add them together. They're not head to tail. They're tail to tail. So I can't add A and B. I could say,
Could you say B plus C equals A?
oh yeah, so B, which has an arrowhead up there, and C, they are oriented head to tail. So I could say B plus C equals A. Ah. Because if I start here for B, I follow B, then I'm at the beginning of C, I go all the way to there. So it's the same as going from here straight to there. So the arrowhead for A is already in the right place and make it equal to B plus C. But I'm supposed to express,
Then you just do the regular algebras.
yeah, so I can do sort of like an algebra thing here. It's going to be, I can subtract B from both sides. Woohoo! So vector C equals A minus B. Nice. Question 4. For the vector equation, find the position at t equals 2. So, little explanation here. This is an equation that tells you a position as a function of an initial position plus a velocity times time. This question is asking you to do nothing more than evaluate this expression when t is equal to negative 2. So I can write this out exactly the same way, except when I get to t, I'm going to write negative 2. Now I've got a scalar multiplied by 3, negative 2, so I'll evaluate that. Negative 2 times 3 is negative 6. Negative 2 times negative 2 is 4, plus 2, negative 1, equals negative 4, comma 3. And that's my final answer. So what it's saying is we've got a particle, an imaginary particle. It starts when t equals 0. It's at 2, negative 1. And when every second that goes by, positive time, we add a 3, negative 2 to it. This question's actually weird. It's asking you about what happened in the past when time was negative. It's like a time machine that goes backwards. So 2 seconds before it started, it's at negative 4, 3, whatever that means.
Why did
Prior to this year, we've been using a notation for vectors that came from an old textbook that we used. There are a couple different ways that people commonly indicate vectors in component form, and a popular way is with the angle brackets. And so we decided this year to adopt the angle brackets. This review test is from last year, so it wasn't changed over. This year, everything that we're doing new should have angle brackets for vectors. It's very nice because it makes it clear whether a series of numbers is indicating a point or a vector. It's a position or a vector. Glad you noticed. Third page. Planes and vectors. So question 5, find two different planes that are perpendicular to the vector 2, negative 3, 1. The vector. So first of all, plane equation has this form AX plus BY plus CZ equals D. And it turned out in our classwork when we looked at this, a perpendicular plane is one where you take the components of the vector and you drop them in as the coefficients of the plane equation, which is really convenient. So, for example, 2x minus 3y plus z equals d. Now, that's part of a plane equation. That actually describes an orientation of a plane. If you imagine a series of planes as like a stack of paper, all parallel, each piece of paper is parallel to the other one. The value of d is what determines which piece of paper in the stack you're talking about. For our example, we only need two different planes that are perpendicular. We don't even care about specific points that the planes have to go through. So what we can do here is use any number we want for d. So I could say 2x minus 3y plus z equals 1. Or 2x minus 3y plus z equals negative 35. Okay. So those are two planes parallel to each other. Now, one question that I didn't get to is like, well, if this is perpendicular to the vector, this is perpendicular to the vector. We haven't actually said that they're parallel to each other, but kind of makes sense. Every plane that's perpendicular to the vector will be parallel to each other. Question 6 is asking the same thing from a different direction. Two different vectors that are perpendicular to the plane. So we can run this process in reverse. We can take the coefficients of the plane equation and use them as the components of a vector. Two vectors that are perpendicular to the plane. If we know one vector, asking for two vectors that are perpendicular is also the same thing as saying, if you find the first vector, find another vector that's parallel to that vector. And because it's parallel to that vector, it will automatically also be perpendicular to the plane. So we have a trick for finding parallel vectors, which is, for example, double everything. So those are two vectors, parallel to the plane. Seven. Let L be the line through 5, 2 with direction 1, comma 2, negative 2. So we're finding here a vector equation. Oh, an equation of L in vector form, or vector equation. So it's going to be in this form x comma y equals something. And normally what we do is we will have a piece of that equation that is standing in for representing velocity. So direction and velocity are kind of the same thing for us. So we're going to be using this direction as if it's a velocity. And we know that it goes to this point 5, 2. It would be convenient for us to just say, oh, that's the position when time equals 0. So our vector equation incorporates the idea of time. And what we're doing is saying we're making a model of a point that's moving through space in a straight line. And because it's moving, it's at different positions at different times. When time is equal to 0, this point's going to be at 5, 2. So we'd write the velocity, 1, negative 2, as a vector, times t, and we'll add the position vector for when time is equal to 0. So, again, when t equals 0, this part of the equation disappears because t is equal to 0. So at t equals 0, the position is 5, 2. So that means it satisfies us that the line goes through 5, 2. Every second that goes by, we're adding 1, negative 2 to this position. That gives us the direction of 1, negative 2. So that one line there is the equation in vector form. Now, part B says, get this equation in parametric form. All that means is take this vector equation and look at it as just the x's and then just the y's. So I've gone through and I've underlined in this equation the x parts, and I'll write them as a separate equation. X equals 1 times t plus 5. And then I can do the same thing for the y part. There's the y. I'm underlining the y pieces. And I'll write those as an equation. Y equals negative 2t plus 2. So those are the equations in parametric form. Now, to find the equation, so those are again describing the motion over time. For any time, you can figure out the x position and the y position. If this particle is moving through space and leaving a trail behind, that trail would be a straight line. This question is asking you, well, what would the equation for that line be, just in terms of x and y? Cartesian equation, x and y. So to do that, we've got equations here that are in terms of x and t and y and t. So we can rewrite these in t equals form. T equals x minus 5 and t equals y minus 2 over negative 2. So I just took this equation, rearranged it to get it so it's in t equals form. So for this last piece, what I'm really doing is saying, okay, for these two equations, x and y, let's set t equal to t. Should be the same thing. So that means that x minus 5 equals y minus 2 over negative 2. And I can multiply both sides by negative 2. I'll get negative 2x plus 10 equals y minus 2, or y equals negative 2x plus 12. And so that's the slope-intercept form of the line that represents the trail that the particle leaves behind as it moves along the page. Questions? Okay, again, so a vector equation has a t in it. Parametric equations have t's in them, saying how the thing moves as a function of time. Cartesian equation is static. It doesn't have any motion. It's just a line, and has just x's and y's. Question 4 is complicated. So we're talking about a sphere and a tangent plane, and this could also be just like a circle and a tangent line. And you had this concept in geometry that a tangent line is perpendicular to the radius at the point of tangency. So if you draw a radius to this point where the tangent line meets the circle, that angle formed between the radius and the tangent is 90 degrees. So in 3 dimensions, this is also true, that the radius in 3D is going to be perpendicular to a plane that's tangent at that point where that vector hits the surface of the sphere. So we're going to show this is true for a particular radius vector, 1, 2, 2, and for this sphere, x squared plus y squared plus z squared equals 9. So that's a sphere with a radius of 3. And we're going to pick any 2 points in the tangent plane and show that that radius vector is perpendicular to the vector AB. So first things first, we have a vector, and we're asserting that the tangent plane will be perpendicular to it. So we can find the equation for a perpendicular plane from perpendicular to 1, 2, 2. So we're going to do the same trick where we take the components of the vector and use them to form the coefficients of the plane. So we come up with a plane equation that says x plus 2y plus 2z equals d. So that defines a plane with a certain orientation. The specific plane that's actually tangent to this circle is going to be the one that also goes through the point 1, 2, 2. So this equation for the sphere is showing us that the sphere's center is at the origin. And this radius vector could also be viewed as starting from the origin, in which case the point of tangency is going to be 1, 2, 2. So the point, the known point, is the point 1, 2, 2. So if you have a plane equation with a d, you can take a known point, plug it in for x, y, and z, and calculate the value of d. So in our case, this would be plugging in 1 plus 2 times 2 plus 2 times 2, which equals 9. So our plane equation is going to be x plus 2y plus 2z equals 9. So that is the specific plane that's perpendicular to our radius vector and which goes through the point 1, 2, 2. That's tangent to the sphere. All right, so we've got an equation for the plane, x plus 2y plus 2z equals 9. Now we want to pick any 2 points in that plane, call them A and B. So looking at this plane equation, can you think of an x, y, and z triplet that works in that equation? Any ideas? No? So 2, 4, 4 would be like taking the radius vector and extending it, making it twice as long, so it actually would be definitely outside the plane. Sorry? So one trick would be to say, if you've got a plane like this, you're trying to come up with some points that are in the plane, go for the x, y, and z intercepts. They're easy to find. So for example, the x-intercept would be where y and z are equal to 0. So that would be the point 9, 0, 0. For b, we could find, oh god, we get a decimal. Oh, let's go for it. So we could say for the y-intercept, we'd have y equals 4.5. So 0, 4.5, 0. So those are 2 points. If you take those and plug them into the plane equation works. So those 2 points should lie in the plane. From those, I'm going to form the vector AB. So this would be going from A to B, or taking B's coordinates and subtracting A's. So that would be negative 9, 4.5, and 0. So that's the vector that goes from point A to point B. So finally, what I need to do is show that that vector AB is perpendicular to R. And we have a test for finding out if 2 vectors are perpendicular. See if they equal to 0. See if the dot product is equal to 0. Right. So we'll do R dot product with AB. So that means taking the x component of AB, multiplying it by the x component of R. So that would be negative 9. And we'll add the y component of AB times the y component of R. That's going to be plus 9. And then we'll take the z component of AB multiplied by 2. Well, the z component of AB is 0. So there is no third part. I just have negative 9 plus 9, which is 0. So, therefore, R, let me go back and dot product equals 0. Therefore, R is perpendicular to AB. It works. All right. Number 2, a unit vector is a vector with length 1. So for a vector v, if the magnitude of v is 1, then v is a unit vector. Find a unit vector that's parallel to the radius vector in question 1. So the radius vector in question 1 was this 1, 2, 2. So we just need to find a vector that's parallel to this that has a length of 1. If we knew how long r was, we could find a parallel vector by multiplying it by like 1 over that length. Well, let's see. What's the length of r? Magnitude of r would be the square root of 1 squared plus 2 squared plus 2 squared, which is 3. Okay, so the magnitude of r is 3. r is 3 units long. So we need a unit vector for this that's parallel. So we need a vector that's 1/3 the length of r and in the same direction. How do you find vectors in the same direction? That's a parallel vector. If you can multiply r by some number, we'll have a parallel vector. So the number to multiply it by is 1/3. So if we take 1/3 of r, r's length is 3, 1/3 of r should be a vector with length of 1. It's 1/3 of vector 1, 2, 2, which is just 1/3, comma 2/3, comma 2/3. So there's a vector that has the same direction, orientation as r, and its length is 1. It's a unit vector. Question 3. Find the equation of a plane that's perpendicular bisector of the line segment joining A and B. So we've got A and B as a line segment. Perpendicular bisector, so there's going to be some midpoint of this line, and we want to find an equation for a plane that's perpendicular. Oh yeah, it should be easy. So I know how to find perpendicular planes if I have a vector. In fact, if I had a vector AB going from point A to point B, and I found a perpendicular plane for that, that would be a plane perpendicular to that line segment. So vector AB is a vector that goes from A to B. And that would be -4, comma, +2, comma, 2. So in other words, to go from A, which is 2, the x component's 2, to -2, you'd have to go down by 4. To go from -3 to -1, you'd have to go up by 2. From 4 to 6, you have to go up by 2. So AB, the vector AB is -4, 2, 2. A perpendicular plane for that vector would be one that has those numbers as coefficients. So -4x plus 2y plus 2z equals d. So I'm almost there. I need to figure out what d is. So to figure out what d is, I need coordinates for a point that's on the plane. I've labeled this point where this line segment intersects the plane and call that M for the midpoint because it's the bisector. How do you find a point that's midpoint between A and B? So from A to B, the x coordinate of a point that's midway between A and B is going to be a value that's midway between 2 and -2, right smack in the middle. So right in the middle between 2 and -2 is 0. In the middle between -3 and -1 is -2. Between 4 and 6 is 5. What we're doing is finding the averages of the x components, the averages of the y coordinates, the averages of the z coordinates for A and B. And that gives us the midpoint. So this is a point that we want to be on our plane. That means we can take these coordinates and plug them into our plane equation. So -4 times 0 plus 2 times -2 plus 2 times 5 equals 10 minus 4, or 6. Which means, finally, I can take my equation here and erase the d and say that that's 6. So there's my final plane equation. That's perpendicular to AB, and it's a bisector of AB. All right, one last question. You guys are doing really well. Keeping up with this, I hope. Question 4, we're going to find the vector equation of the ray that starts at t equals 0 seconds at negative 1, 3. So there's a point. Passes through the point 7, 7, 4 seconds later. So we're going to go from here to there, and we're going to do it in 4 seconds. So we can think of this going from negative 1, 3 to 7, 7 as like a vector that jumps from one place to another. The length of the vector is 4. So that vector, if we call this A and B, vector A and B, vector AB would be 8, 4. So to go from negative 1, 3 to 7, 7, you'd have to increase x by 8 and increase y by 4. And we do that in 4 seconds. So the velocity is going to be this divided by 4. We want to know how much does it move in 1 second. This is how much it moves in 4 seconds. So our velocity vector is going to be 1/4 of that, which is the vector 2, 1. So that represents our velocity. So we can write a vector equation xy equals, we'll put in our velocity, 2, 1 times t plus the position at t equals 0, which is negative 1, 3. And that's our final vector equation. And what that means is, if we took and substituted 4 in for t and evaluated this, we'd find ourselves at the position 7, 7. All right, folks, that's it. We got through one whole period, the entire thing. You're great. Have a great day.